Where is the hottest place in the universe? As far as we know, it's in England, right here. Just south of Oxford, in a place that feels like the modern day equivalent of where they cracked the Enigma code, there are some seriously bright people who have built the hottest place in the universe. Effectively, it's a star in a box at a whopping 200 million degrees C. Now that number is far too hot to really mean anything to me at all. But I will tell you this, the centre of the sun is 27 million degrees, which is also pretty much completely meaningless to me. Did you know that it only takes light 8 minutes to get from the sun to the Earth, but it takes it thousands of years to get from the centre of the sun to the edge of the sun? I won't go into why that is now, but the brilliant Randall Munro once did a calculation to show that a lizard gives out heat faster than a lizard-sized piece of the centre of the sun. I wish we could hear the sun. Said nobody ever. It would be awful. If sound could travel through the vacuum of space in the same way that it travels through the air that we breathe, it would take 15 years to get from the sun to us. And when it did, it would sound like a chainsaw right next to our ears all the time, day and night. So why have these big names near Oxford built a star-making machine? It's because this is the world centre of fusion research. They invited me to visit a few weeks ago. It's surprising how many people don't know that fusion power is actually working. Now we're just working on making it cheaper. In a moment, I'm going to show you an unbelievably cool video of the inside of a working fusion reactor, but first, let's talk about fusion. Some of you will know this already, so in very brief summary, fusion is sort of like squeezing together two grapefruits in order to try to make a very hot melon. It's very difficult to do, which is a very, very small part of the reason why this is not working now. For hundreds of years, people have been trying to change lead into gold. That's called alchemy. But it's crazy difficult to change chemical elements into other elements because you have to go into every single atom and change the number of protons that every single one of them has. We're not even nearly technologically advanced enough yet to be doing alchemy. We can switch between chemical elements in a very few special cases, but even then we're not really fully in control of it. The key idea to understand about switching between chemical elements is that the most stable element in the entire of the periodic table is iron. This means that theoretically, elements that are smaller than iron can be squeezed together in order to release energy. That's called fusion. And it also means that elements larger than iron can be pulled apart to release energy as well. That's called nuclear fission. I already made another episode about that called Nuclear Disasters and Radioactive Batteries. Watch that after this one if you haven't already. In stars, hydrogens fuse together to make heliums, releasing an F-ton of energy. Just south of Oxford, we've managed to build a box called JET, which does the same thing, squeezing hydrogens together to make helium. And it's been really difficult. It's all well and good having a load of hydrogen, but you need something literally the size of the sun before the central particles will be crushed into one another under the weight of the hundreds of thousands of kilometers of other particles on top of them. The breakthrough for us humans, not having much room for a star, came when we realized that if we heated these particles up enough, then they might smash into one another at such incredible speeds that they might just fuse anyway. And so we made a machine that could reach 200 million degrees, and it worked. It might look like a lot of it is very empty, but actually it's crazy hot in there. And you see those white flecks on the screen? That's where neutrons being thrown off by the reaction have damaged the otherwise incredibly durable camera. Those high-speed neutrons are really dangerous to living things, which is why we have to surround the whole of our fusion reactor with incredibly thick concrete walls. It's also why we use gaming tech to control robots inside the reactor to do the maintenance work. Engineers stand outside the concrete shields with VR headsets on, and then they use robots that copy the movement of their arms to do the maintenance work. As these neutrons fly out of the reactor, going straight through the inner walls as if they're not even there, don't worry though, they don't make it through the concrete shields, they heat up a lithium metal blanket that's wrapped around the edge of the reactor, and that heats up water, which is used to drive turbines. Seriously, if you have a better way of turning heat into electricity than just using steam to drive turbines, I want to work with you. So back at the 200 million degrees inside the box, at these ridiculous temperatures, we need to use super strong magnetic fields to suspend the hydrogen in midair away from the walls. Otherwise, the heat of it would vaporize the walls. You might be thinking how hydrogen, which is barely magnetic at all, can be suspended by magnetic fields. The trick is that when it gets to this crazy hot temperature, all of the charged bits separate apart from one another. It becomes something called a plasma, and that means it can conduct electricity. We can then induce a huge voltage in the donut, which will cause it to have its own magnetic field. And so then it can be suspended by our magnetic field. What this means is that not only is the donut at millions of degrees, but it also has hundreds of thousands of amps of electricity racing around it too.
Sounds suspiciously like something dangerous.
But it really isn't. The big difference between traditional nuclear fission and nuclear fusion is that nuclear fission occurs in a chain reaction. Most of a nuclear fission power plant is designed to slow down and keep the reaction under control, which means that if things go wrong, then they can go very wrong. With fusion, it's the opposite. Almost everything in the design is there just to try to keep the reaction going. That's why it flickers, because it's just so difficult to sustain. If anything goes wrong in a fusion reactor, it just stops immediately.
Now, in case you want to build your own nuclear fusion reactor, here are some key things to know. Firstly, there's only a minuscule amount of hydrogen ever actually in the reactor. 1 gram of hydrogen releases the same amount of energy as 14 tons of coal. Secondly, it's not just normal hydrogen that we're using, it's heavy hydrogen with extra neutrons. This is normal hydrogen, and these two are heavy hydrogen, deuterium and tritium. We can get deuterium from the sea. There's a silly amount in there. And we can get tritium from the lithium blankets that surround the reactors. Conveniently, as the neutrons bombard that lithium, some of the lithium turns into tritium. Suspiciously convenient. As for what to build your reactor out of, I know that it can be tempting to build it out of graphite, what with its amazing heat-resistant properties. I know how tempting it is, but don't succumb. It absorbs the fuel. Instead, it's much better to 3D print it with tungsten.
Thanks for watching, spread the knowledge, deliciously subscribe for more, and remember that you can follow me on Instagram and Snapchat at Matthew Shribman.
If you have a science question about this episode or anything at all, send it my way and I'll try to get it answered for you.